Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from Scratch in Golang, where we dive into what the neural network is and we implementing neural network from the scratch, like all of the things purely in Golang. And to do this, we're using this book called Neural Networks from Scratch in Python. But again, as you can guess from the name, we're not using Python, we're using Golang. And in previous videos, we dived into what we kind of remembered some math. So we studied the derivatives, we studied the gradients, partial derivatives, and the chain rule. And all of this we will need for the implementation of the backpropagation, which is, and the goal of this will be that once we do the forward pass through the model, we need to understand what is the contribution of each neuron to a specific input. For example, we have an input, we have the output, and we had randomly initialized the weights and the biases for the model. And then once we did the forward pass, which is sending the input and grabbing the output, then we need to understand the contribution of each neuron and, well, each parameter, actually, because the neuron has weights and bias. And as far as the book tells us, that's where we will need to calculate the derivative, so the partial derivative for our big function, which is the neural network. And finally, we going to implement some code. So let's go. I think this is, I'm just scrolling through the chapter. Looks like the big one. And I see a lot of the code, which is good. So not this one. Okay, backpropagation. So let's go. Working. Okay. No, this. What? Main. Okay. Now that we have an idea of how to measure the impact of variables of a function's output, we can begin to write the code to calculate these partial derivatives to see their role in minimizing the model's loss. So the idea that through the model training, we want to understand how we should change the weights and biases to improve the loss in the accuracy. Before applying this to a complete neural network, let's start with the simplified forward pass with just one neuron. Rather than backpropagating from the loss function for a full neural network, let's backpropagate the ReLU function for a single neuron and act as if we intend to minimize the output of this single neuron. We're first doing this only as demonstration to simplify the explanation, since minimizing the output from the ReLU activated neuron doesn't serve any purpose other than the exercise. Minimizing the lost value is our end goal, but in this case we'll start it by showing how we can leverage the chain rule with derivatives and partial derivatives to calculate the impact of each variable for the ReLU activated output. We'll also start by minimizing this more basic output before jumping to full network and overall. So probably that will be, we'll start from the from a simple example. So this is one neuron. Let's quickly recall the forward pass and atomic operations that we need to perform for this single neuron and ReLU activation. We'll use an example neuron with 3 inputs, which means that it also has 3 weights and a bias. So this is the X, we have the W, which is the weights, same amount as the input values, and we have bias, but well, same amount as the input values, because it's kind of three neurons No, one neuron with 3 connections to the 3 inputs and 1 bias. So this is the single neuron, right? We then start with the first input X and read the related weights W. Okay. We have to multiply this input by weight. Okay. So visually, yeah, we have, this is the input, we have the I think, well, at least for me, this representation is a little bit confusing. I don't know if I can make the better one. So, no, do I have this? Okay. So this is the input, right? This is the neuron. Then where's the line? We have the connection, right? And no, this one. And we have something like this, but I don't have dot. Oh, I have. And I need text. Where is it? It's a little bit smaller. Okay, let's do this. Okay. So for me, the input is this one. This is the input. The weight is here. It's like on the edge, right? Then we have the bias, which is the here. And then we have the output value, which will be, inside the neuron, right? So that will be here. Okay. For me, this is easier to understand because then, for example, we will have another input plus bias, and then we'll have the final result here, and that will be, like this, like another input to the second layer. We repeat the separation for, okay, so we basically have, this is really confuses me because I want to move it. It's not that easy to draw it here, but I mean, another and another, and we have this, and we have this one, then we have second, third, and inputs, right? So the second one is -2, minus. Third one is 3, 12, the weight -1, 2.0, and here we will have the result 6. For me, this is easier to understand. I know I don't know, maybe for somebody this is easier, but for me this is the X, this is the weights, because they're connected to the neuron. This is the bias, which is the one thing, and then we have the result value inside the neuron, because it will be the input for the second one. So all called together, I don't want to write this for now. Let's see, but yeah, basically we're having a dot product between two vectors. Dot product? No. Oh yeah. And plus bias. This forms the neuron's output. The last step is to apply the real activation function on this. So then we check the max, comparing 0 and non-zero values. And yeah. Okay, so they show it as a multiplication. Okay, now it makes more sense. Okay. And then we have the ReLU that shows this neuron. So this all forms a neuron, and it's an activated neuron because it passes through the ReLU function. Right. This is full forward path. Let's treat all of these chained functions as one big function which takes the input values x, weights, and bias as inputs and the outputs y. So we will have the function from the three variables. This big function consists of multiple simple functions. There is a multiplication of input values and weights, some of these values and biases, as well as the max function as the ReLU activation, three chain functions in total. We have multiplications, then we have sum, and then we have the max. The first step is to backpropagate our gradients by calculating the derivatives and partial derivatives with respect to each our parameters and inputs. To do this, we're going to use the chain rule. Recall that the chain rule for a function stipulates that the derivative of the nested functions like. So we calculate the derivative over the input values. Oh, no, just an example. Okay. This big function that we just mentioned can be, in the context of our neural network, loosely interpreted as ReLU from sum of inputs multiplied by weights plus bias, and then from all of this the ReLU takes place. Or in the form that matches code more precisely is ReLU from. Our current task is to calculate how much each of the inputs, weights, and a bias impacts the output. We'll start by considering what we need to calculate from the partial derivative of first weight for the example. But first, let's rewrite our equation to the form that will allow us to determine how to calculate the derivatives more easily. So we have multiplication, oh, interesting. Okay, so they defined a sum as a function from three inputs, where each input is another function, which is multiplication, actually four. Three functions and the bias, and then the ReLU is the function from this. The above equation consists contain three nested functions: the ReLU, a sum of weighted inputs and bias, and multiplications of the inputs and weights. To calculate the impact of the example weight, this one, on the output, the chain rule tells us to calculate the derivative of ReLU with respect to its parameter, which is the sum. So we'll take the... So we'll calculate the derivative for the ReLU function, then multiply it with partial derivative of the sum operation with respect to its this one. So we will ignore, then multiply this with the partial derivative of the multiplication operation with respect to x0 input. Let's see in a simplified equation. I need to calculate the partial derivative of weight 0, for example. Why we have an x here? I mean, I thought that we will... I thought it will be the d over d w0. Why it's dx? Why we need to respect the x0, not the... I mean, well, in that case I understand how we ended this one, but why we're not doing it d over d w0? Because in that case it will be the same, right? The rule the sum, the rule over the sum over the multiplication between x0 and w0, and then we'll have the multiplication over the w0. For eligibility, we did not denote the ReLU parameter, which is the full sum. Eligibility, we did not denote the ReLU parameter. We did not denote, which is this full sum and the sum parameters, which are all of the multiplications of the inputs and weights. We excluded this because the equation won't be longer and harder to read. This equation shows that we have to calculate the derivatives and the partial derivatives of all of the atomic operation and multiply them to acquire the impact that x0 makes to the output. For me, it still doesn't make sense. We'll start by considering what we need to calculate for the partial derivative of w0. How we end up with the x0? We can then repeat this to calculate all other remaining impacts. The derivatives with respect to the weights and the bias will inform us about the impact that will be used to update these weights and bias. The derivatives with respect to inputs are used to chain more layers by passing them to the previous function chain. We'll have multiple chained layers of neurons in the neural network model, followed by a loss function. Want to know the impact of a given weight or bias on the loss? That means that we will have to calculate the derivative of the loss function, which we'll do later in this chapter, and apply the chain rule with derivatives of all activation function and neuron in all the consecutive layers. The derivative with respect to the layer's input is opposite to the derivative with respect to the weight. The derivative with respect to the layer's input as opposite to the derivative with respect to the weights and biases is not used to update any params. Instead, it is used to chain to another layer, which is why we backpropagate the previous layer in the chain. Okay, I had to take a break. I had to take a break because my son wasn't sleeping and I needed to help to calm him down. So yeah, let's go. I'm not sure if it was, if you heard the sound of him or not, but let's continue. Derivative with respect to the layers input. This statement, I cannot. Derivative with respect to the layers input, as opposed to derivatives with respect to the weights and bias, is not used to update. So we have and I still don't understand. So here we're calculating it was said that we're calculating the derivative with respect to the params, but why we're using the input here? So I don't know. Maybe with the code it will be more clear for me. I do understand what it says, but I cannot match it with the example that I have here. During the backward pass, we'll calculate the derivative of the loss function and use it to multiply with the derivative of the activation function of the output layer, then use this result to multiply by derivative of the output layer and so on through all of the hidden layers and activation functions. Inside these layers, the derivative with respect to the weights and biases will form the gradients that we will use to update the weights and biases. The derivatives with respect to the inputs will form the gradient to chain with the previous layer. This layer can calculate the impact of its weights and biases and loss property. To be honest, very hard to read. Maybe I don't need to read it a couple of more times. Maybe something visual. For example, let's assume that our neuron receives gradient 1 from the next layer. We're making up this value for demonstration purposes, and the value of 1 won't change the values, which means that we can more easily show all of the process. We're going to use the color of red for the derivative. Why it's not going chain? Why the value of 1 won't change the values? Okay. Recall the derivative of the ReLU with respect to its inputs is 1 if the input is greater than 0, otherwise it's 0. So okay, yeah, we can DReLU dz if that is greater than 0, then 1 else 0, where this variable means the ReLU function with respect to z. We use z instead of the x from the equation, since the equation denotes the max function in general, and we're applying it to the neuron's output, which is z. Okay. The input value of the ReLU function is 6, so the derivative equals 1. So we're taking the... Wait. Oh, so the... Well, derivative of the real function with respect to its inputs, it's 1. Oh, okay. So because the real function itself, need to clear it. So the real function itself is relu is x if bigger than 0 else 0, right? So this is like f from x, right? And we have x, but the derivative in that case will be 1 if bigger than 0 because it's x itself. And okay, so and if we calculate the derivative for the input value, this is why we get the 1, because the input value of the result. Okay, so we calculate the output value for the neuron, applied the ReLU activation function, which ended up with the 6th value. Right now we're going, I guess, backwards. So we taking the ReLU derivative, which is 1 in case the input value is bigger than 0, which is the case. This is why the ReLU functions in the derivative. Okay, then it makes sense for me. We have to use a chain rule and multiply this derivative with the derivative received from the next layer, which is 1 for the purpose of this example. Once again, using the chain rule, you have to use it and multiply this derivative, this one, with the derivative received from the next layer. Which is 1 for the purpose of this example, but I don't get it. Let's assume our neuron receives a gradient of 1 from the next layer. We're making this for the as the value, which means that we're going to use the color red for derivatives. Recall that the derivative the derivative from the next layer. What is the next layer? This one? This is... yeah. Okay. Multiplying inputs by weights, adding weighted inputs and bias, ReLU activation function backward pass. The derivative from the next layer of d value equals 1. I mean, I understand that it came up, but it would actually easier to understand if it was the normal value, so we can backtrack it. And okay, we have the previous, assuming that we have some previous already calculated derivative value, and we are multiplying it for the ReLU activation function derivative, which is 1 multiplied by 1, it's 1. This is result with the derivative of 1. Okay, so this... I don't... Moving backward through our network, what is the function that comes immediately before the activation function? I really don't understand what is the next layer. Okay, so they mean that there is... Okay, this part is really not clear. Okay, so they kind of assuming that this is the next layer. What happens? This is the head. And this one value comes from the next layer. So we're kind of in the middle of the backpropagation, right? This is okay. So then we have the sum function, and we need to calculate the gradient for the sum function, right? It's a sum of weighted inputs and bias. This means that we want to calculate the partial derivative of the sum function and then use the chain rule, multiply this by the partial derivative of the subsequent outer function, which is ReLU. We will call this result psi. The partial derivative of the ReLU is the first weight, this one, right? This is the derivative, the partial derivative of this value and this value. Partial derivative of the ReLU with respect to bias. Okay. The partial derivative of the sum operation is always 1. The partial derivative of the sum is always 1, no matter of the inputs, because d over the x, we have this 1. This, as we treat it as a constant, the derivative of the const value is 0. Okay. The weighted inputs and bias are the weighted inputs something says, so we'll calculate the partial derivative of the sum operation with respect to each other, multiplied by the partial derivative of the subsequent function using the chain rule, which is the ReLU function denoted by ReLU dz. ReLU dz denoted this one. For the first partial derivative, we have the d sum over d weight. I mean, here we have the d from weight 1. We have the 1. Okay, so we have the partial derivative of this function. Okay, we have a partial derivative of this function with respect to this value. We have a sum of the things, and the sum of the things always is 1. To be clear, the d sum to above means the partial derivative of the sum with respect to x input weighted for the first value of the inputs and weights. 1 is the value of this partial derivative, which we multiply using the chain rule with the derivative of the subsequent function, which is the ReLU function. Okay, again we have to multiply the chain rule and multiply the derivative of the ReLU function with the partial derivative of the sum with respect to the first weighted output. Okay, so we have the forward pass, multiplying then we have the sum of the multiplication, we have the ReLU, then we have the okay, so we have the d value, which we derivative from the next layer. We assume that we have something next, and it's 1. Then we calculate the derivative for this one, which is okay, based on the z. But that was equals to 6, so this is the 1. The partial derivatives of the multiplication, the chain rule. So we have the first one is partial derivative of the sum itself. Then we take in the previous derivative value multiplied by this one. So again we have 1, 1. So this is 1. Okay, so we have, so we have the partial derivative of the sum function with respect to first pair that forms the multiplication, right? Partial derivative of the function with the first way. This result with a partial derivative of 1 again. So this is the 1. Then I guess we need to calculate the partial derivative of the x and y, right? And w. We can then perform the same operation with the next white input. So we have, okay, same, and well, second, again 1, right? How it will be with the bias? Oh, so the sum against the bias. Oh, correct, because if I would take the derivative with respect to b from this, we're assuming this is const, this is const, this is const, so they will equal to 0, and then we have the derivative from the input value, well, input variable itself, and without any multiplications it will be 1. Okay. Continuing backward, the function that comes before the sum is the multiplication of weights and inputs. The derivative for a product is whatever the input is multiplied by. Recall. Yeah. So for example, in this case, if, for example, the derivative for weight will be the corresponding x value, the derivative for corresponding x value will be the first weight, right? Right? The partial derivative of f with respect to x and y equally. The partial derivative of f function with respect to y equals x, following the source, the partial derivative of the first weighted input with respect to the input equals the weight, the other input of this function, because we have 2. Then we have to apply the chain rule and multiply this partial derivative with the partial derivative of the subsequent function, which is the sum. We'll calculate it. So now, when I studied the FastAI course, they had like the backpropagation, but they don't dive too much into like how exactly this works. And I mean, with this explanation, even what sometimes it's not clear for me, well, how it's written, but right now it makes more sense why it's called backpropagation, because I mean, I kind of understood the idea that we need to, after the model training, we need to adjust weights based on how the batch passed. But I mean, this is much better. Oh, well, I mean, in the FastAI course, they telling that they're trying to not to dive too much into details in some places, because they focusing more on actually practicing things. But I think some things was not clear for me still. This is good time to point out, as we apply the chain rule in this way, working backwards by taking the ReLU derivative, taking the summing operations derivative, multiplying both, and so on. This process is called backpropagation using the chain rule. As the name implies, the resulting out functions gradient passed back through the neural networks using multiplications of gradient of subsequent functions from the layer the current one. Let's add this partial derivative to the console. So we have this chain of values, partial derivative of the multiplication of the chain. So this is the partial derivatives of the multiplication. No, it's partial derivatives of the sum operation, not the... It's clear, the sum, and then we calculate... Up here it should be written here, or partial derivative, well, of the weights itself, because right now we have the derivative value for multiplication against input equals to. So for example, here, for this multiplication, the derivative for the x will be -3, but for weight it will be 1. Yeah. This multiplication and chain rule gradient for the first input. We perform the same operation for other inputs and weights. Multiplying inputs by weights. Oh. Okay, so so at this, I mean, in the sum, we okay, and for example, let's assume that this, I mean, this is just one neuron, and we have so many. Assuming that the x is actually a neuron from the previous input, a neuron from the previous layer, and it means that we will calculate the, for example, here we're using the 1 as value from the previous, not the previous chain, and for example, in some cases it will be -3. This is the complete set of activated neurons' partial derivatives with respect to the inputs, weights, and bias. How it will work with the dense layers where every neuron connected with everyone. That's the complete set of activated neurons partial derivatives with respect to the inputs. Recall the equation from the beginning of this chapter. Since we have the complete code, as we're applying the chain rule from this equation, let's see what we can optimize in these calculations. We apply the chain rule to calculate the partial derivative for the ReLU activation function with respect to the first input in our code. Let's take the related lines of the code and simplify them. So, partial derivative for the multiplication is as a weight. ReLU. But we had the ReLU in here. Oh. Oh. How they jump? So the rule. This equation starting from the left-hand side is the derivative calculated in the next layer with respect to its input. This is the gradient backpropagated to the current layer, which is a derivative of the ReLU function and the partial derivative of the neuron's function with respect to x input. This is all multiplied by applying the chain rules to calculate the impact of the input to the neuron on the whole function's output. The partial derivative of a neuron's function with respect to the weight is the input related to this weight. And the input related to it, and with respect to the input is related weight. Partial derivative of the neuron's function with respect to the bias is always 1. Multiply them with the derivative of the subsequent function, which was 1 in this example, to get the final derivatives. We're going to code all of this. Oh, so we calculated all of the derivatives, right? But right now we need to calculate the derivative for the ReLU activation function against the input. And this is the... So we're taking the derivative of the ReLU against sum multiplied by derivative of the sum against the multiplication and multiplication against the x1, right? So we have the ReLU. I mean, this is the multiplication of this one. This is the ReLU, just this one and this one. Well, I would say if they wrote it as a 3 multiplications, well, 3, like 2 multiplications with the 3 params, it will be a little bit easier to combine. So yeah, like this. So that's this one, this is this one, and this is this one. So we have the 1, right? The ReLU dz multiplied by the weight. So the ReLU function is the value multiplied by, what's the value? No, it's previous one, right? D value. What's D value? D value DDD. Yes, the derivative from the next layer. Well, it's from the next layer, but for the backpropagation, it's kind of from the previous one. So we have D value. This is the from the next layer, but it's just the previous computation from the during the backpropagation. Then we have a function that represents the derivative for the ReLU, and it returns input value if it's greater than 0. So for example, so to indicate that the neuron was activated, and then it's multiplied by weight. So for example, if the output is negative, so that will turn into 0. We're going to got all of these derivatives in the dense layers class and the ReLU activation class for the backpropagation step. So I guess, well, we have the dense layer, we have the forward, probably we'll have the backward, and then I have the real loop. Probably we'll have the backward, something like this. Right. Altogether, the partial derivatives of all combine into the vector make up our gradients. Our gradients could be represented as dx, gradients on the input, so that's the values, gradients on the weights, gradients on the bias, just one bias here. Okay, for this single neuron example, we also won't need our dx. With many layers, we'll continue backpropagated to preceding layers with a partial derivative with respect to our inputs. Continuing this single node example, we can now apply these gradients to the weights. Continuing, this is typical the purpose of the optimizer discussed in the following chapter, but we can show a simplified version of this test by directly applying a negative fraction of the gradient. We apply a negative fraction of this gradient since we want to decrease the final output value, and the gradient shows the direction of the steps. Yes, the gradient shows where it moves, well, the direction, and we need to change it. For example, our current weights and biases are this, and we're applying a fraction of this to the weights. And then we can go for the next batch, right? Now we're slightly changing the weights and bias in such a way as to decrease the output somewhat intelligently. You can see the effect of our tweaks on the output by doing another forward pass. Yeah, I'm just checking how far away. Okay, where is it? We can then apply a fraction of the gradient. Yes, then we slightly change the weights. Okay. We can see the effect of our tweaks on the output by doing another forward pass, multiplying, okay, by adding the ReLU, and we successfully decreased the neuron's output from 6 to this value. Note that it does not make sense to decrease the neuron's output in the real neural network. We're doing this purely as a simple exercise, but I think we'll be decreasing something else. We want to decrease the loss value, which is the last calculation in the chain of calculation. So, like here, we're decreasing the inputs, the neurons, but as it said in the real life, we will be optimizing against the lost value, so that will be increasing the loss value. Now we'll apply the one neuron example to the list of samples and expand it on entire layer of neurons. To begin, let's set a list of 3 samples for the input, where each sample consists of 4 features. For this example, our neuron will consist of a single hidden layer containing 3 neurons, list of 3 weights and 3 biases. 3 weights and 3 biases. We are not going to describe the forward pass again, but the backward pass in this case needs further explanations. So I will stop here. So it means that tomorrow we'll continue with implementation, probably of the backward path. And yeah, we'll be able to reuse the dense layer class that we had before. I think for now that's the good time to stop, as we messed around with the backpropagation and dive into how it's working. Okay, but for now, I see you tomorrow. Bye bye.